All right, so this is our screencast on the binomial theorem exploration. So this is basically to see some traits about the binomial theorem to make it easier for us as we get into our lesson in the next screencast. So go ahead and start by doing the first 5, which is practice of arrangements that we talked about in the previous screencast. All right. Here you can check your answers. So here's the first 4. And here is, these are numbered incorrectly. Okay, because there's an A and a B. And here's the last 2. Okay, so we do have to reflect on the arrangement screencast lesson. So it says yesterday, it wasn't necessarily yesterday, we finally explored a formula for arrangements, and I say formula in quotes because it was more of a exploration in itself, with and without repetition. Revisit the bags problem. So we looked at this bags problem yesterday, and it said with 2 bags, what was the sum of all the possible combinations? So we could split screen with our notes from yesterday, but just to remind you, the possible combination is that you can get x times x and an x. There's 2 ways to get an x and a y, and then there was 1 way of getting a y squared. For 3 bags, there was 1 way of getting x times x, or x cubed. There was 3 ways of getting 2 x's, or x times x and a y. There were 3 ways of getting an x and 2 y's, or x times y squared. And there was 1 way of getting 3 y's. Okay, and what about 4 bags? So for 4 bags, there was 1 way of getting x 4 times. There were 4 ways of getting x 3 times and a y. There were 6 ways of getting 2 x's and 2 y's, or x squared, y squared. There were 4 ways of getting an x and 3 y's. And there was 1 way of getting, I don't need to put the 1 there, right? There's 1 way of getting y 4 times. And then lastly, make sure I wrote that down right. We had 1 way of getting x 5 times. There were 5 ways of getting x 4 times and y once. There was 10 ways of getting x 3 times and y 2 times. There was 10 ways of getting x 2 times and y 3 times. There was 5 ways of getting x 1 time and y 4 times. And then 1 way of getting y 5 times. You might be saying to yourself, wow, you have an excellent memory. But I actually am doing expansion in my head. You should be seeing a pattern here. So let's actually take these and put them all here, right back to back so you can see them all. So here's 5 bags. And here was 4 bags. Copy, paste, just so that they're all on the same page so we can see the pattern if you didn't recognize it yet. Copy and paste. And copy and paste. Okay, a lot of dead air there. Okay, so it says look at our answers from above. So let's look for patterns here. So how do the exponents of x change? So let's get a highlighter color out. I'll use yellow. So if you look at the exponents on x, this is a 2, this is a 1, and there's 0 here. 3, 2, 1, 0. 4, 3, 2, 1, 0. 5, 4, 3, 2, 1, 0, right? So if you notice, the exponents on the x values, or the first term, is decreasing by 1. So that's part of why I was able to do it so fast from memory, right? I knew that was happening. How do the exponents of y change? So if we look at the y values and their exponents, So there's no y's here. Looks like a 1, but there's no y's there. There's a 1 and there's 2. None, 1, 2, 3. None, 1, 2, 3, 4. None, 1, 2, 3, 4, 5. So if you look at those, I wasn't touching anything there. 4, 5, yes it was. Those are increasing by 1. So on the second term, they were increasing by 1, the exponent that is. What do you notice about the sum of the exponents of each term? So the sum of the exponents, this was 2 and 0, which is 2. This is 1 and 1, which is 2. And this is 2 and 0, which is 2. This is 3, 2 and 1, which is 3, 1 and 2, which is 3, and 3. 4, 4, 4, 4, 4, 4, 4. And then 5, 5, 5, 5, 5, and 5. So the sum of the exponents is equal to the amount of bags there were. And then lastly, what about the pattern on the coefficient? So this is harder to see. I think I'm actually going to go down to Pascal's triangle in order for you to see them after I try to explain this here. But if you look at the coefficients, like obviously this is 1 and 1, this is 1 and 1, 1 and 1, 1 and 1 here. So there's 1s, right? But then we have a 2 here, so where did that come from? Right? I'll have to explain that, but this 3 and this 3. So what you can see, it's part of Pascal's triangle here, is that we can get that 3 by taking this number plus this number. We can get this number by taking this number plus this number. So that's why I had you write them all on one page here. So this 4 comes from this 1 plus 3. This 6 comes from this 3 plus 3, and you get it from the previous row. Okay? So we're going to write it down for now, adding from the previous row, but we'll actually expand on that after we do our next section. Adding coefficients from the previous row. All right, now it says let's take a break from this for a second just to do this right here. So let's take a break from the bags to learn this formula. So this formula says NCR, which is n number of objects choosing R at a time. You could also write it like this. And to evaluate it, what you're going to do is you're going to take n factorial, so the number of objects, factorial, and then divide that by the number of objects minus R times R factorial. Okay, so you'll see the pattern very shortly. If it looks like the formula is confusing, you'll see it right when we do it here. Okay, so this is 2, choose 0. So one way of also is just thinking about it. So if I had 2 objects, how many different ways can I choose 0? Well, 1, because you can just choose 0, right? But how it's done using that formula is 2 factorial over, and then I do 2 minus 0, which is 2 factorial, and then R factorial, so 0 factorial. Remember, 0 factorial is 1, and anything divided by itself, which is this right here, is 1. So this is equivalent to 1. Box it too. So this is 2 objects. How many different ways can I choose 1? Well, I can choose the first one or the second one. So it's 2. But how do I get that? 2 factorial divided by 2 minus 1, which is 1 factorial, and then just this R value, which is 1 factorial. When the numbers are more than 2 and 1, it's much easier to see the formula. But that's 2 divided by 1, which is still 2. And then 2 choose 2. So if I have 2 objects, how many different ways can I choose 2 of them? Just one way. So the answer to this is 1. But the math behind that, 2 factorial. 2 minus 2 is 0 factorial. And then just R is 2 factorial. That's 1 also. So if you look, these numbers should look familiar, 1, 2, 1, right? So I'll summarize this when we're done getting these. Okay, so 3, how many different ways can I choose 0? That's just 1, but the math behind it, 3 factorial, and then you do 3 minus 0, which is 3 factorial, and then r, which is this value factorial, and you get 1. 3 factorial over 3 minus 1 is 2 factorial, 1 factorial. So 3 factorial is 3 times 2 times 1. 2 factorial is 2 times 1, so this is just 3. And then 3 choose 2 is 3 factorial over 1 factorial. Oops, that's just a factorial. 1 factorial times 2 factorial, which is the same thing. I did that math wrong. No, I didn't. I did it right. It's just the same thing as the last one that we just did. It's just the denominator switched. And then 3 choose 3 factorial over 0 factorial, 3 factorial, which is 1. And notice that it's the same math. These two have the same math, and these two have the same math, right? Okay, so let's keep that in mind, that that's happening. And so let's just do this problem 3 times instead of doing it 5 times, right? So I know I'm going to get 1 here, but just so we realize why, it's 4 factorial over 4 factorial divided by 0 factorial, which is 1. All right, and it's the same math here, so 1. 4 choose 1 is 4 factorial over 3 factorial times 1 factorial, which is 4. Remember, that's 4 times 3 times 2 times 1 divided by 3 times 2 times 1, so that's just 4. And I'm going to get the same thing here. And then this one is 4 factorial over 4 minus 2 is 2 factorial, and then 2 factorial. And then that is, if you want to do it mental math, I'll also show you how to do it in your calculator. 4 times 3 times 2 times 1. And then divided by 2 factorial, so I can get rid of these two. And divided by 2 more factorial, which is 6. So that's 6. Okay. And yes, you get to use a calculator for all of this, but mental math is good also. So this is 1 and 1, right? Let's see if we can use that idea of, we know that this is giving our exponents 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. If you don't remember it from above, remember you get it by adding the 2 previous. So if I add 1 and 4, this is going to be 5. If I add 4 and 6, this is going to be 10, 10, 5, 1, right? And it has that symmetric pattern going on. Why are these answers familiar? Why are we doing that? Those are coefficients from the problems that we did before, right? So these numbers, and it's used for binomial expansion, okay? This is called Pascal's triangle. So this is when n equals 0, n equals 1, 2, 3, 4, 5, 6. We're going to do 6 rows. So it starts off with a 1 right here in Pascal's triangle. And then the outsides are all 1. So if you wanted to go outsides all the way down, you could, but I don't want to. All right, and then this is 1, sorry, that's just 1, 1. My bad, the 2 does not go there because where would I get a 2 from? Then I add these 2 together and I get 2. So it's just, the top is a triangle of 1s, right? 1, 1, 1. And then 1, 2, 1. 1, add those 2, that's 3. Add these 2, that's 3. 1. 1, add these 2, that's 4. Add these 2, that's 6. Add these 2, that's 4. 1. 1, add those 2, it's 5. Add those 2, it's 10. Add those 2, it's 10. 5, 1. 1, 6, 15, 20, 15, 6, 1. And notice it's symmetric every time. And this continues on and on and on forever. And this is going to give our coefficients when we're expanding a binomial. All right, and we'll look more at that in the next lesson.